Okay, thank you. In this episode, we're gonna study reaction kinetics. Reaction kinetics means usually to reduce the solute concentrations. In mathematics, it is usually given as first order ordinary differential equations such as dc over dt equals to negative k times c. So this is the first order reaction, simply because it is e to the power of 1. So in general, we could say it is equal to negative k sub n to the power of times c to the power of n. That is actually the nth order. Okay, so we will start from zeros to the second order. Usually, n is actually zeroth order, first order, and the second order. There are many, but these are three typical reaction orders that most of textbooks and papers, research papers, are dealing with. So we are actually considering the batch reactor. So batch reactor means you have reactor which is somehow closed, and this one has zero concentration, so you actually put certain amount of mass m of solutes, and then the reactor contains V of water. So once you add certain mass m of solute, which means pollutant or contaminant, your initial concentration C0 would be mass over volume. Okay, so this concentration would be most likely milligrams per liter, or it could be mole per liter if you convert it. Right. So if in the batch reactor there's no flows, Q equals 0 in batch reactor. So we have initial volume of water, such as this much, and then you add mass m, then you get the initial concentration C sub 0. Afterwards, this chemical start with reacted. In other words, concentration change with respect time equals to negative, let's say first order Kc. So how this concentration decreasing? So we initially add certain amount of reactant in here. So once this solute is coming in, it is reacting with already dissolved reactant, and the solute concentration decreases, such as this. So, and the initial condition is at E equals 0, C 0 equals to C naught, as we defined in here. So let's just solve this first order reaction. So if I rewrite the covering equation in a different form, that would be dc over c equals to negative k dt. You could integrate both sides with respect to concentration c and time t. So once you integrate, t equals to t is from 0 to time t, and at t equals 0, concentration is c naught. At t equals t, you have certain concentration c. If you integrate left hand side, that will be natural log of C from C naught to C. And then the right hand side is nothing but KT. So it could be written as natural log C minus natural log C naught equals to negative KT, or log C equals to log C naught minus KT. That is somehow the linearized equation. For equivalently, you could say C equals to C naught exponential negative KT. Doesn't really matter which form do you get as a conclusion, but we will pay attention for this because in most cases that at time t and concentration C is measured. So 0, 1, 2, 3, blah, blah, blah. And these concentrations are actually measured. So, but we do not know what reaction order is. And the reaction order is still unknown. So what we do is we check whether this reaction follows the first order or not. So having in this equation, we will set the natural log C is y, and then x as t as x. So if you have this plot, then your x-axis is time t, and your y-axis is natural log of C. Okay. So in that case, as concentration is decreasing with respect to time, if this reaction follows the first reaction, then the graph would look like this. And then you could somehow draw the straight line. Okay, I can draw. Yes. In that case, your intercept, that should be natural log of C naught, because you already know C naught, and identifying this position is straightforward. And then if this line or data points are kind of linear, then you could say this slope is nothing but K, which is in here. Therefore, if a reaction is first order, then you plot natural log C versus time t, and then your intercept should be natural log of C naught, initial concentration, and your slope would be negative K. So this is how we estimate K value, reaction constant K, is intercept. Assuming that this reaction is first order. There could be a case that unfortunately that your data points looks likely this, then you could conclude that, oh, this reaction looks like linear when time is early. However, at the end, it is deviating from the straight line. So you should conclude that the reaction is not the first order. But if you have this clear indication that all the data are nearby the straight line, which is fitted line, your intercept is natural log of concentration, initial concentration, and your intercept, sorry, slope is the reaction constant. Okay? Sometimes we do not know C naught because if the data is available from certain intermediate position, then intercept can also give you estimated initial concentration. But the key point is slope is negative K, making sure, after you make sure that all the data are aligned in this log C versus time plot. Okay, Okay, the next one is the first zeroth order, number 2 zeroth order. That is, again, that the general representation is dc over dt equals negative kn c to the power of n. Zeroth order, that n equals to 0. So I should say dc over dt equals negative k0. So you multiply dt both sides and integrate from time 0 to t. So your left hand side should be dc c0 to c. Your right hand side should be k sub 0 integration dt from 0 to t. So if you integrate left hand side, that is c at given time t minus c naught equals to negative k0 times t. So finally, what you're going to get is concentration is decreasing from initial concentration C naught with K0 times T. So this is actually the final equation. And note that K sub 0, in other words, K0 times T should have concentration of C because it is comparable with the C naught. Okay? So in other words, it is milligrams per liter. So K0 is not 1 over time, but K0, unit of K sub 0 should be milligrams per liter times 1 over time. So in that case, you could plot your right hand side, you could also plot time t, and your left hand side as ct as a y. In that case, your data should look like, or if you observe this line, and you could draw a straight line, which is like linear regression. And you could obviously say that your intercept would be C naught, initial concentration, and then your slope, that is negative K sub 0. So in that case, you could actually try something kind of different. So in other words, you actually have time t, and then you have concentration data. And so far, you could plot two things. One is time t and c t, just concentration itself. And if it shows a linear line, then you could conclude that this reaction is zeroth order. Or if you plot x-axis as time t, but y-axis natural log of concentration, and if it gives like linear line, then that one, obviously, this reaction equals to first order. Okay. So your x-axis is always time t. For your y-axis, you try concentration itself, or you try the natural log of concentration. If one of them matches better, then you could conclude that the reaction follows whichever better matching. Now, you could actually try second order. So in other words, dc over dt equals negative k2 c to the power of square, or c square. So the reason I use a subscript is this k value is, the unit of this k is changing with the order. So if you reorganize it, then c dc equals to negative k2 dt. You integrate from this one from 0 to t, and then c naught to c. Okay. So if you integrate 1 over c squared, that would be negative 1c, and c0 to c, that is negative k to t. Okay. So since you have both sides, you have a negative sign, you can just cancel it out. So final form is C 1 over C minus 1 over C naught equals to K2T. You could add 1 over C naught in both sides and saying plus. Okay. So in this case, you could actually have another plot. So you have T and your y-axis is 1 over concentration. And at t equals 0, that point is 1 over C0. The C0 is the highest concentration, assuming that reaction makes solutes like um, disappear. So in that case, if you have 1 over C as y, then 1 over C naught would be intercept. Then K2 would be slope. Since it's 1 over C as t increases, then this point should increase. While the concentration C is decreasing, 1 over C should increase. So in that case, your slope would be K2. So you, whenever you have data, you plot these three. So in this case, this reaction is second order. So again, whenever you have this experimental data T versus concentration, you made these three plus C versus T, log C versus T, 1 over C versus T. Okay. So find out the data or graphs that gives you most linear case, and then you could determine the reaction order. So if I reorganize everything, then you have zeroth order Ct equals to C naught minus K sub 0 times T. And then first order, that is natural log of C equals to natural log of C naught minus K1T. Then the second order is 1 over C equals to 1 over C naught plus K2T. Okay. So again, the key point here is you make in your right hand side t is linear, t to the power of 1, and then change your y-axis to have a linear t on your right hand side. So zeroth order, it is concentration itself. First order, it is log of concentration. Second order, it is the 1 over c. It doesn't really matter. You use here either natural log c or common log 10c. Doesn't really matter, but natural log always gives a simpler representation. Okay, so try to remember this. Okay, now we could just make this case somehow general. So you can just think about general case. This is number 4, nth order. So in this case, Tc over Tt, again, that is negative k sub n, c to the power of n. You can reorganize it like c negative n Tc equals to negative kn Tt. You integrate it. So if you integrate this, then that is actually, you actually need to add 1. So c the power 1 minus n, 1 over 1 minus n. If you differentiate this, then that would be c to the power of negative n. And then that is from c naught to c. Then your right hand side is always linear to time t, negative kn t. Okay. So assume that like n is greater than 1. So then you could say your left hand side would be 1 over c n minus 1 minus 1 over c naught n minus 1 equals to negative kn and positive n minus 1 t. Now you multiply c naught to the power of n minus 1 and reorganize it, then you could say C naught initial concentration, which is constant, divided by concentration at time t, the power of n minus 1 equals to 1 plus S of n minus 1, C n minus 1 t. Okay, so this is actually the nth order reaction, time dependence. Okay. So um, you could actually generalize it. So in this case, it is better not to use this one for n is not equal to 1. So if n is not equal to 1, then you could use this, and you could determine n value and also the reaction constant. So our goal for this reaction analysis is to find out value of n and reaction constant. Yep, that's it for today. But this is somehow the extra which works for any n, but not equal to 1. There are mathematical tricks that you could make this reaction equation working for n, but that is too much. So here we have 3 reactions, reaction order, and each case that if the concentration is decreasing, then you actually have these 3 forms that you need to keep in mind. And again, the most important thing you shouldn't forget is this is for batch. In other words, you have certain reactor, and then here the volume is V, and your initial concentration is C naught. And as time goes on, C is decreasing. So there's no input, there's no output. Okay, so batch is isolated system, and we can just let it start and measure the concentration T at given time T. That is what batch is. Okay, so it's kind of similar to we have a cup of water, and then you put either salt or sugar, then stir it and just let it dissolve. Although the salt is not reacting, and case is like this. You have initial volume of water, and then there's no additional input and then no additional output. And then everything is working or reacting within this volume without input and output. That is what batch reactor is. So all of these reactions that we discussed today is for the batch reactor. Okay, that's it for today in this reactor analysis. Thank you so much.